Good morning or good afternoon or good evening, ladies and gentlemen, and thanks for listening to my talk. My name is Laura de Lorenzis. I'm professor of computational mechanics at ETH Zurich, and I'll be talking about modeling and simulation of damage and fracture in construction materials with a special eye on concrete. First of all, I'd like to thank the organizers of this conference for inviting me to deliver this plenary lecture. And secondly, I'd like to acknowledge that my co-workers did most of the work, and they are listed here. In particular, here there are a few people who were part of my group at the Technical University of Braunschweig, Roland Kruse and Tao Wu. And there are other people who are part of my current group at ETH Zurich, Pietro Carrara, Jonas Heinzmann, and Akanksha Mishra. Okay, let's get started. Let me give you first a brief outline of what I'm going to present. I'll start with an introduction, then I'll focus on phase field modeling of damage and fracture, which is the framework that we've been using for this work. So I'll start with some basics regarding the framework, and then I'll outline some quantitative validation efforts. Then I'll focus on the application to concrete, and in particular to concrete at the mesoscale. I'll motivate the reason for this choice later. And here I'll show some experimental issues and how we solve them, focusing on X-ray tomography and in situ testing. And I'll show you the very first results on simulating real concrete. And finally, I'll outline briefly some possibilities to extend the current model to more complex problems, including coupled problems and fatigue. And I'll draw a few conclusions and show a brief outlook. Okay. So damage and fracture modeling is a relatively recent field of research. If you think that there have been approximately 100 years of fracture theory and approximately 50 years of fracture computations. So compared with, let's say, the general strength of materials approach, this is a younger field. The first seminal work on fracture mechanics is the paper by Alan Griffith, who was 27 at the time, and it's a paper of 1920, which is why 2 years ago it celebrated its 100th birthday. So what is the basic idea that Griffith pioneered? He said that if you have a pre-existing crack, say of length A, at critical conditions, the release of elastic energy due to the advancement of the crack by dA, let me see if I can point to this. So at critical condition, this release of elastic energy must be equal to the consumption of energy, which is due to the creation of the new surfaces. And he postulated that the unit energy per unit, let's say the energy per unit surface area that is needed to create new surfaces is a material property. And this material property was called critical energy release rate or fracture toughness, and it was given the name of GC, where G was in honor of Griffith. Now, much later, the finite element method became very popular, and the first applications of fracture mechanics for computations with the finite element method started about 50 years later. So this is considered one of the seminal papers in 1971. And it turned out that computations in fracture mechanics were particularly challenging. The theory itself is also challenging for different reasons. One of the reasons is that this is, mathematically speaking, a free discontinuity problem. So where there's a crack, there's a discontinuity in the displacement field, which is the field we solve for in mechanics problems. And we don't know upfront where the discontinuity occurs because we don't know upfront where the crack is, which is why we call this a free discontinuity problem. On the other hand, another issue is that cracks can be very complex in geometry and topology due to phenomena such as crack kinking, crack branching, merging, fragmentation. And so for all these reasons, it's very challenging to this day to perform computations in fracture. There have been a number of approaches that have been proposed over the course of the years. I here, without meaning to be exhaustive, I'm just categorizing them simply into three categories: the category of smeared crack approaches, the category of sharp crack approaches, and the category of lattice approaches. So smeared crack approaches are the approaches where we do not have discrete cracks propagating through the specimen. So you may be familiar with damage mechanics models in which basically we are solving for a damage field, which you see represented in this example. These approaches do not need to track the discontinuities, but have the disadvantage that they may not be able to realistically reproduce true crack patterns. You see in this example, for instance, that in a classical three-point bending specimen, you may have that the damage field grows fat overloading rather than propagating as a crack would do. And sharp crack approaches, on the other hand, can be exemplified by mentioning the extended finite element method, XFEM, or the generalized finite element method, or cohesive zone approaches using interface elements. Now, all these approaches have the disadvantage that they need to track the discontinuity, so to track the cracks. Cohesive zone models are very efficient if you know upfront where the crack is, which, however, is not always the case, is actually rarely the case. And the XFEM and GFEM, they are giving good results in 2D, but their implementation becomes extremely cumbersome and extremely complex in 3D. And lattice approaches also have their own drawbacks. They have issues in being really predictive as they need for the general case, let's say, for cracks of arbitrary topology and geometry. So as usual in computational mechanics, no approach has really only pros or only cons. So each approach has strengths and weaknesses. And in this context, I'll try to place the approach that I'm going to talk today, which is no exception. It will also be shown to have some weaknesses, but I believe that the list of the strengths is way more significant. And the approaches that I'm going to talk about, as I mentioned, is the so-called phase field modeling approach for damage and fracture. So before I get to the phase field modeling approach, let me briefly talk about the variational reformulation of Griffith theory, which is due to Francfort and Marigot in 1998. So Francfort and Marigot introduced an energy functional with two arguments: the displacement field and the crack set gamma C. So you see here that this total energy is comprised of three contributions, the third one being the potential energy of the external load, which is not that interesting. So I'll focus on the first two contributions. The first contribution is the elastic strain energy, and the second contribution is the fracture energy. And according to Griffith postulates, the fracture energy is considered to be the product of GC, which is a material property, times the measure of the crack set, which in 2D is the length of the crack, and in 3D is the surface of the crack. Now, the variational reformulation of Griffith theory consists then in the minimization of this energy functional under the constraint that the crack set can only grow. Now, of course, this crack set is also the domain where U has a discontinuity. From a numerical standpoint, minimization of this energy functional is basically intractable. And this is why a major step forward was performed in the year 2000 when Bourdin, Francfort, and Marigot proposed a regularization of the variational reformulation of Griffith theory. And this regularization led to what is nowadays called the phase field approach. Now, the difference between the variational Griffith approach and the phase field approach is that the crack in the phase field approach is no longer a so-called sharp crack, as you see exemplified in this figure, but it's a so-called diffusive crack. So we are approximating the crack through the steep variation of a field, which we call D. And you can think of this field as a damage field. This field is equal to 0 when the material material is intact, and equal to 1 for the material that is fully damaged. So basically at the axis of the sharp crack, one can say. And so the steep variation of D between 0 and 1 is reproducing the crack in a smeared or diffusive fashion. And you see that the support of the region where D has values that are significantly larger than 0 is proportional to a length scale, which is a characteristic size, a characteristic length involved into the model. Now let's look at the functional, the regularized functional here, which is now no longer a function of U and has no longer as arguments U and gamma C, but U and D. And once again, we have 3 contributions to this energy: the elastic strain energy, which now includes this degradation function G of D, which is coupling the 2 fields with each other and is degrading the elastic strain energy as a result of the damage. Then we have the fracture energy, which is no longer proportional to a measure of the crack set, but is now a volume integral, just like the elastic strain energy. And it contains a so-called local damage dissipation function, W of D, and a gradient of the damage. You see that since we went from a surface integral to a volume integral, now we have a length scale coming into the picture, which is precisely the length scale I was mentioning before. And you see that we still have a proportionality factor GC, just like in the sharp crack model. And now it is through the minimization of this functional that we derive the governing equations that will allow us to solve a fracture problem basically through the solution of a set of governing PDEs. And so basically it is the minimization of this functional which will give us our governing equations, and the governing equations, while once solved, will give us the field of the damage, and this will then show us immediately where the cracks are propagating and how. This minimization is again a constraint minimization, because again, to be sure that cracks cannot heal, we have to make sure that D can only increase. Now, it has been shown through very nice mathematical tools, in particular gamma convergence, that if else tends to 0, the minima and the minimizers, under some assumptions that I don't have time to talk about, of the regularized problem converge to those of the variational reformulation of Griffith. And intuitively here, you can see that as L tends to 0, we become closer and closer to the original sharp crack condition. But on the other hand, it has also been shown by Pham and Marigot and Maurini that this method, this model can be, the phase field model can be also constructed as a special family of gradient damage model. Indeed, you see here that we have the gradient of the damage, but this is a special family of gradient damage models which are, let's say, variationally consistent and which have this additional gamma convergence property to the sharp to the sharp formulation, sharp crack formulation. Okay, now I haven't told you the entire story, because if you were using this functional and performing the constraint minimization of this functional and deriving from this the governing PDEs leading to the solution of the problem, you would have a symmetric behavior in tension and compression, which is typically not realistic for brittle materials. Here we are talking about brittle fracture the whole time. So that's why an actually more realistic version of this model is obtained by the so-called decomposition of the elastic strain energy density into 2 contributions, and this can be done in several ways. One of which is considered to be driving the damage, and it's indicated here as psi plus, and another one is considered not to be driving the damage. Okay. Now, overall, what are the key advantages of this framework? This framework has become now really popular in the engineering community. So, as I mentioned, the very first paper appeared in 2000, so it's already 22 years old, but it took about 10 years until this paper started to become known in the engineering community. And since then, the interest has picked up really very, very rapidly. And by now, this approach is very well known, and it's starting to have also the first industrial application. Why is the interest in this method so dramatically increasing? What are the key advantages? In my view, the key advantage is the flexibility of this approach. You can basically describe initiation, propagation, merging, branching, so arbitrarily complex topologies of the crack, all in one unified setting. This because you're describing this field and you are describing it automatically through the solution of the governing equations that stem from minimization of this functional. So you can deal with arbitrarily complex crack topologies without any extra ingredients which are meant to lead to the expected results for merging, branching, and so forth. So there is a great flexibility, which is kept also when going from 2D to 3D. The framework has mathematical advantages connected to its variational nature. I don't have here time to expand on this aspect, and implementation is very simple, even in 3D. On the other hand, there's no free lunch. You may imagine, since we have very steep variations of this phase field, that to resolve this steep variation within a finite element discretization, you need a quite fine mesh, which leads to a quite high computational cost. And on the other hand, this functional, the regularized functional, is non-convex with respect to both arguments simultaneously, and this leads to some issues in the efficiency and robustness of the solution procedures. I don't have time to focus on these aspects, but with my group, we've been tackling some of these issues also recently. Now, to show you what I mean when I talk about flexibility, let me show you these two videos. I won't tell you yet what is this because I'm gonna bring these two videos on another slide much later in the presentation. But I just would like to point to your attention that here we are seeing hundreds of little cracks propagating, intersecting, branching in a 3D setting in a fully complex, topologically complex fashion. And this is all straightforward to reproduce with the phase field approach. Now, one of the first issues that people looked at when the phase field approach started to become popular in the engineering community was the issue of validation. And validation in the early days was performed in a qualitative way, meaning people would look at the crack patterns and be happy when the pattern was reproduced satisfactorily. But quantitative validation means that also the corresponding forces or force displacement curves need to be reproduced accurately, and ideally even local measurements, full field measurements should be reproduced accurately. So I'd like to show you for this reason one campaign of quantitative validation that we carried out in collaboration with Andrea Karpiuk-Presakari and Dr. Poncelet at INS Cachan. Andrea was a PhD student at the time, and from my group side, this was work by postdoc Tao Wu. And so at Cachan, they have very impressive possibilities to conduct stable fracture tests using a multi-axial electromechanical testing machine, an hexapod with multiple degrees of freedom, so that you can apply arbitrarily complex loading histories by controlling different degrees of freedom independently from each other. And since they also have the possibility of full field displacement measurements using digital image correlation, they could even use these DIC results as drivers to adjust the application of the loads. And so they developed an algorithm which they called multiple input, multiple output integrated DIC that was able to control loading in such a way to apply a very complex loading history. I'll show you some curves shortly. And this led to the crack being able to propagate stably and in a quite complicated manner. Okay, and they did this on the 3 specimens that you see here with notches of different geometries. So we used this test campaign for quantitative validation of the phase field model for brittle fracture. There is one of the beauty of the model is that there is a minimal set of parameters which you need to calibrate. So 2 are the classical linear elasticity parameters for isotropic materials, elastic modulus and Poisson's ratio. Another one is the tensile strength. So we determine these parameters through independent testing. And then we have the fracture toughness GC and the length scale involved into the phase field model. Now for the fracture toughness GC, we were basically reproducing with the phase field approach the 3-point bending notched tests that had been performed experimentally. And so we could calibrate GC based on a comparison between experimental and computational 3-point bending tests. And finally, another nice feature of the phase field model is that one can give a physical interpretation to the length scale, which I don't have too much time to expand upon. But what is maybe essential to say at this stage is that it's possible to find a relationship between the tensile strength of the material, the elastic modulus, the fracture toughness, and the length scale. So after having measured the tensile strength and calibrated the fracture toughness and measured the elastic modulus, is it basically possible to compute the length scale? Okay, so then based on the fully calibrated model, we could blindly predict results of these complex interactive mixed mode fracture tests that were carried out in Cachan. So here you see only some representative results. You see on the top row the contours of the horizontal component of the displacement field. And you see here that as a result of the complicated and stable loading history, we have that the crack first stably propagates upwards, then at some point it changes direction and starts propagating downward. And then at some point, again, it starts changing direction and starts propagating again upwards until shortly before failure, it branches into 2 branches having different directions. And these all stably, and this corresponding to complex loading histories, which I show you shortly. Here on the bottom row, you see the predictions, the totally blind predictions of the finite element method discretizing the phase field model. So you see that the trend, so this is a displacement field, and you see that, of course, a discontinuity in the displacement, which is visible by naked eye, corresponds to the location of the crack. And here you see, again, that the crack is exactly reproducing the behavior that is seen experimentally. So the first change in direction, the second change in direction, and finally the branching. Now, if we look at the specimen from the outside, we see the final crack pattern. We don't see the branching from the outside. However, a closer analysis looking inside the specimen reveals that the branching, which was visible in the DIC results and also in the phase field results, this is a close-up of the notch region, is present also in the tests, although it's not visible with naked eye from the outside. And on top of that, the angle of this branching is very, very similar to what is measured through the phase field approach, predicted through the phase field approach. And finally, I promised to show you the complex loading history. So here you can see the time change of the normal force and of the shear force. So you see that in the first stage of loading, both normal force and shear force are increasing and then decreasing. Then follows a second phase where the normal force is led to decrease and the shear force is led to increase. In the subsequent phase, it's exactly the opposite. The shear force decreases and the normal force increases, and so forth. So there are several phases in the behavior of the specimen, and it's particularly impressive for me that, and this is really the quantitative part of the validation, that the agreement between experimental and numerical force versus time relationships is quite good, considering that this is a blind prediction and considering the complexity of these mixed mode tests. Now there's a second validation exercise that I'd like to briefly talk to you about. This is not yet concluded, but is in progress. And this is the so-called damage mechanics challenge. It's a challenge organized by Purdue University in collaboration with the Sandia and Lawrence Livermore National Labs in the US. It started some months ago, and with my group, we decided to take part. The bulk of the work, the heavy lifting, has been done by Jonas Heinzmann, who's actually a very young master student in the group. And he was supported by basically half of the group, those especially working on fracture. And so while I'm speaking, results of this challenge are not yet known, but in the moment you will be watching this video, results will have been already made available, presented. They will be presented on December 13 at the annual fall meeting of the American Geophysical Union. What was the objective of this damage mechanics challenge? The objective was to predict fracture in 3D printed gypsum specimens, 3-point bending specimens. I'll show you the geometry in the next slide, with different notches located in different positions and with different geometries. So there have been two phases in this challenge. In the first phase, some data were given, some experimental data were given for calibration of a damage or fracture mechanics model. And in the second phase, a blind prediction is taking place by the groups taking part in this challenge, and this blind prediction will be then compared with the true experimental results of these additional tests, and the comparison will be then again shown on December 13. Here you see the finite element mesh for the 4 specimens involved in the calibration phase. You see that they're basically all 3-point bending tests with notches. So here we have a centered notch. Here we have an offset notch and another offset notch with different distances from the center. And here we have a skewed notch. Plus there are additional specimens, actually one additional specimen that of which one has to perform the blind prediction. And here you can see close-ups of the experimental and computational surfaces of the crack at the notch. Let's say above the notch, so the crack propagating above the notch. And I can show them from this perspective, which is basically easier, which is a bit easier to appreciate, I think. So you see that the agreement between computational and experimental surface is very, very good, except for the upper portion of the crack, but only for this case, which is probably to be explained by the fact that in this region there are significant compressive stresses. I'll come to this much later in the talk. But we were basically very satisfied by the possibility of calibrating the phase field model to such an agreement that we could reproduce these fracture surfaces to a very good level of quality. You can appreciate the 3D effect of twisting of the crack surface, which is generating by the offset and by the skewness of the initial notch. And this is, again, another perspective where, again, you can appreciate the three-dimensional effects due to skewness and off-center location of the notch. Okay, and I cannot show you more because, as I said, the exercise is still in progress. So hopefully there will be more to come soon on the blind prediction, for which we don't have results yet. Now, all I've been talking about this thus far was related to homogeneous materials, brittle and homogeneous materials. Now, I'd like to make the next step and show how we are proceeding to apply this framework to concrete, and in particular to concrete at the mesoscale, and I'll be more precise shortly. Now, you all know better than me that concrete, one of the most important construction materials, is a multi-scale material. If we look at it macroscopically, it may seem homogeneous, but if we zoom in, we will see that, in fact, concrete is constituted by aggregates, pores, and the cement matrix. And some people would add the interfacial transition zone to this count of phases. And if you zoom in again and look at the cement matrix in more detail, you can also visualize, ideally, like in this sketch, the different constituents of the cement matrix. Now, conventionally, I'm going to call mesoscale the scale at which we resolve aggregates, pores, and cement matrix, and possibly the interfacial transition zone. And I'm going to call microscale the lower scale at which we resolve the different constituents of the cement matrix. Now, which scale is important, or which scales are important? The answer, in my opinion, is it depends. It depends on which phenomena we're interested at. So the recent literature has shown that, for instance, if you are interested in degradation of concrete due to, for instance, chloride diffusion, then it may be a good idea to take a look at the microscale. On the other hand, if the interest lies on prediction of crack initiation and propagation, or in prediction of fatigue, then the mesoscale may be an attractive alternative to look at. And this is the reason why, for the time being, we in my group, we are focusing on the mesoscale. Now, how to describe concrete at the mesoscale? As I mentioned, we are currently focusing on three phases. So one is the cement mortar, one are the aggregates, and one are the pores. We are, for the time being, we are neglecting the interfacial transition zone. We may incorporate it in the future. But this is not enough. We also need to specify what for us is the matrix and which ones are the aggregates. So we are proceeding in the following way. We are setting a threshold size below which we basically homogenize everything into the cement. This is done because, as you know, aggregates and pores in concrete span an incredibly wide range of scales, and so it will be computationally intractable to resolve all these scales in a computational framework. So this is why, setting this threshold size, we homogenize anything that's below this size into a matrix phase, and then we will resolve independently the aggregates above the threshold size and the pores above the threshold size. Now, what are the steps needed to model and simulate mesoscale concrete? So first of all, we need the geometry description of the mesoscale. And this, as I'll show you in a second, we do through X-ray tomography or computed tomography or CT. And of course, this needs also a substantial phase of image processing. On the other hand, we don't just need the geometry, we also need the mechanical properties of the faces, and we characterize them through mechanical testing. We obviously need predictive mechanical models, and this is the location at which our phase field approach to fracture comes into play. So we use this approach to predict damage and fracture in the matrix. Obviously, the resulting computational framework is very demanding for the reasons I've described before, speaking of the phase field model. So we need efficient numerical methods implemented through massive parallel computing. And finally, we lay a lot of importance on experimental calibration and validation. And this also we intend to do through in situ testing inside the tomograph and digital volume correlation. So basically the 3D version of the digital image correlation that we used for the validation in collaboration with DNS Cachon that I was talking about before. In this slide, you see the basic idea behind X-ray tomography. We have a source of X-rays. These X-rays are sent through the specimen and are then intercepted by a detector, which is basically measuring how much of the X-rays is being absorbed by the specimens. And since the absorption is something that is related to the volumetric mass of the material, or equivalently to the atomic number of the material, different spots in the specimen having different atomic number or volumetric mass will absorb different quantities of X-rays, and so they will give rise to different grayscales in the image that we obtain. It should maybe also be added that each scan through the specimen will give rise to a 2D image, but then the specimen will be rotated inside the CT so that at the end we will have a collection of a large number of 2D images. So each of these 2D images is a radiography. But the collection of all these 2D images will be reconstructed into a 3D geometry through image processing algorithms. And so at the end of this test, we will have a 3D visualization of the heterogeneous specimen. On top of that, what we are making use of is the possibility to apply load to the specimen inside the tomograph. And this requires, of course, ad hoc testing machines. They need to be X-ray transparent. They need to allow for the rotation of the specimen and so forth. But here you see an example. You see a test that has been performed inside the CT in displacement control. You may notice that here at each point that you see here highlighted, there are small load drops, because as we are performing a scan, some time is elapsing, and so there is a little drop in load associated to the time of a scan. Now, in the description of the geometry of the mesoscale, there are some problems to be overcome. And what are these problems? Well, one can subdivide the mesoscale geometry description in two main phases. Phase one is the segmentation. Phase one consists in having this 3D image that I was mentioning before with different grayscales per voxel. A voxel, as you may know, is the 3D version of a pixel. So it's basically a cube associated to a given grayscale. So the first question is, to which phase belongs each voxel? Yeah, so is it a cement voxel or a pore voxel or an aggregate voxel? Yeah, and here one of the issues is the possibly insufficient contrast in case of similar composition and density among the constituents. For standard concrete types, it's quite common that the cements and the aggregates have a very similar chemical composition, which implies that there will be a very low contrast between cement and aggregates. And so it will be very difficult to perform segmentation automatically, which is what one would like to do. And there will be a massive need for operator intervention, which of course prolongs the time of segmentation and makes it a very tedious and time-consuming exercise. On the other hand, the next step, once you have a segmented model, is meshing. So meshing means the setup of the finite element model to be then computed in the next step. And this is also not trivial, because here we have a huge number of particles, and many of them will be very close to each other. So you need to make sure that these particles are described faithfully. So for instance, if they are just in contact, they still need to be separate particles and not be condensed into one. And also you want the number of elements not to be excessive in order to have a reasonable computational cost. And again, this operation is very time consuming and very hard to automatize. Now, regarding the second phase, we are bypassing this phase by performing so-called voxel-based analysis. This means that we are treating each voxel basically as one finite element. So we don't need to worry about the issues related to meshing, but we still have the issues related to insufficient contrast. And now in the following few slides, I'll show you how we have been solving this issue recently. So what is the basic idea? Now, this is work which was performed essentially by Pietro Carrara and Roland Kruse at the TU Braunschweig in collaboration with the group of concrete materials of the TU Braunschweig, and also in collaboration with Dale Benz from the National Institute of Standards and Technologies, the NIST in the US. The basic idea was to increase the X-ray attenuation of the cement mortar by adding some barite powder to it. Now, of course, we needed to be careful while doing this because we did not want to modify the mechanical properties of the concrete. Otherwise, we would run into a problem of altering what we are going to measure through the one of the means of enabling these measurements. So first of all, we made sure that only the finest aggregates were replaced. But then we carried out an extensive series of tests to evaluate whether the mechanical properties were affected. Interested people can find all the details in this paper. The short answer is we found out that the mechanical properties were not affected, which was, of course, a favorable result. We were using quite small amounts of barite, from 0.5% to 2.6%, referred to the total aggregate volume. And now I'll show you the results. Now, these are 2D images which show you the grayscale distribution of a cross-section of a concrete specimen, first without barite and then with increasing amounts of barite. So this last image corresponds to the highest amount, 2.6% of barite. And you can already, with naked eye, see that while in this image, it's basically impossible to distinguish the aggregates from the cement paste. In the last figure, it's very easy to distinguish, and thanks to the addition of the barite. But this is still qualitative, and quantitatively what happens? Quantitatively, what you want to do is automatic segmentation. And one simple way to do this segmentation is to use histograms of, so frequency histograms versus the grayscale values. So here, look first at this red curve, and you see that there are two peaks. One of these peaks corresponds to the air, so the pores, and the other peak corresponds at the same time for aggregates and matrix, which makes it impossible to distinguish automatically between aggregates and matrix. But in the yellow curve, which corresponds to the case with the highest amount of barite, which was the amount that we have been using ever since, here you see that suddenly the aggregates and the matrix correspond to two different peaks. And so it becomes quite easy to automatically segment. So this solved the issue of contrast, and we could finally carry out voxel-based analysis on concrete specimens taken from the tomograph. So these are, again, the videos that I started with a few slides ago, and now I can tell you that this is real concrete added with barites and 2.6%, where we segmented pores, cement matrix, aggregates, and we started by studying a tensile test on this specimen, and the results are the cracks that I've been showing you already before. This is a computationally quite demanding experiment. There are about 100 million degrees of freedom in this test, so you can imagine that one needs really an efficient implementation. Now, this was the starting point. Since then, we've been doing further steps ahead. There was some break in between due to the fact that my group moved from Braunschweig to Zurich. We had to buy the equipment again and recast specimens and restart basically performing tests. There was also significant delay due to COVID. So I was hoping to show you the latest results, but they are not yet ready. But there is intense work in progress. We're using different geometries of specimens at the moment. The objective is to find stable test setups to observe stable cracking, so to be able to track the propagation of cracks during loading. I hope that we will publish soon the first results of in situ testing compared with phase field modeling through the mesoscale setup that I've been describing. Now, I'm heading towards the concluding slides. So I've been talking about brittle fracture and quasi-static fracture, quasi-static testing. But the phase field setting is ideal for more complex setups. Oops, sorry, something is going wrong here with the slides. Let me go back. So the phase field setup is perfect for extensions. And here I'm just showing you two types of extensions. One is the extension to coupled problems. For instance, when you have fracture due to thermal effects or to drying. Here, the examples I'm showing are on soils, on clay materials for the type of simulations that you see on the left, on desiccation. On the right-hand side, this was just a prototypical linear elastic material with thermal cracking. But one could, of course, combine this type of modeling setup with a mesoscale description, or possibly also wants to define or to describe construction materials, also homogeneous materials is one, if one is not interested in the mesoscale details. And so desiccation cracking, for instance, is also a problem in cement or in concrete. And so these tools may be very useful in that setting as well. You see here some three-dimensional results which were obtained by my postdoc Chenyi Luo in collaboration with Lorenzo Sanavia from the University of Padova. And you see that it's possible to analyze in 3D arbitrarily complex topologies of drying cracks and so study the effects of thickness, geometry, material properties, loading conditions in terms, in this case, of evaporation flux and so forth. And here you see that we can reproduce some features that have been observed experimentally, such as the fact that intersecting cracks tend to be perpendicular to each other. So we can really, again, in this case, pursue a comparison with experimental evidence. And one of the recent extensions that we performed is the one to fatigue. Let me see if I can activate the left video. Maybe not, unfortunately. But anyway, yeah, so we have been able to extend the phase field framework to fatigue and recover the Paris law as a consequence of the model, the phase field model, rather than having to input the Paris law from the outset. So if you could see this video on the left, you would see complex cracks due to fatigue propagating all over the place in this specimen. And of course, this has been set up for mechanical type of tests in mechanical engineering rather, but one could think also of applying this framework to fatigue in high performance concrete, for instance, that can be used in bridge or other fatigue sensitive applications. Finally, let me draw a few conclusions and give you a very brief outlook of what we are heading to for the near future. I hope I convinced you that phase field modeling is a versatile and powerful approach to predict damage and fracture in brittle and quasi-brittle materials. I haven't expanded on this quasi-brittle concept, but there have been recent extensions to incorporate not a perfectly brittle, but a less brittle behavior, if desired. So we believe that this framework is very useful for prediction. On the other hand, we also believe that X-ray tomography with in situ testing has a great potential to observe in detail damage and fracture in brittle and quasi-brittle materials, resolving the relevant scale or scales of observation. And we believe that the combination between the two bears huge potential to shed light on the role of mesoscale geometry and constituent properties of concrete on its damage and fracture behavior. But a similar reasoning may be applied to other construction materials. And finally, recently we already at the moment, we are working at a test campaign, a comprehensive one with tomography plus DVC on concrete specimens to observe stable fracture and compare with results of mesoscale modeling. Possible extensions that we will be working at in the near future are to incorporate in the model also the fourth phase, the interfacial transition zone, as I mentioned before. And there may be advances needed for the phase field model to become more realistic. In particular, the description of fracture under significant amounts of compression and shear still poses some challenges. And so this is certainly one of the to-do items for the future. Plus, we may also want to incorporate friction at the crack lips to make, again, the phase field model even more faithful. And finally, I'd like to briefly mention that our in-house code that we use for prototyping, written in MATLAB, but with Fortran Max files, is available for free download. We called it Griffith and can be found at this website. And I'd be happy to answer any questions on this as well. And finally, I'd like to thank you all for your kind attention, and I look forward to the live session for questions and answers. Thank you very much.